Hello, everyone. Welcome to the MIF++ seminar. Today, Professor Gregory McColm, who is the chair of the International Union of Crystallography Commission on Mathematical and Theoretical Crystallography, will talk about graph isomorphism of derived graphs. Over to you, Greg, please.
Okay, hello everyone. Thank you for coming this afternoon or this morning or whatever time you are currently experiencing. I asked to give this talk because we are, the three of us are going to be submitting a paper and we're trying to figure out exactly what to say. It's related to previous talks I've given, but it's also related to a concern that has appeared in other seminar talks, which is how do you identify whatever it is, whatever crystal structure you are presented with. I'm approaching from the other end. Most the talks that have appeared before in this seminar are concerned with you have a particular crystal, you have put it in your X-ray machine, it has given you something that the software presents you, and you are now supposed to figure out what it is. I'm approaching sort of from the other end. I was brought into crystallography by some crystal design people, and so the primary concern for the crystal design people is, what is it that you are actually making? So with that caveat, I'm going to be talking about essentially identifying crystal structures. So the thing is, this is a talk about graphs. And the theoretical computer science, well, computer scientists discovered graphs pretty early in the game. They're very useful critters. In fact, there is a theorem that says anything you can do, any kind of data structure you have can be represented with a graph. So now officially graphs are very recent. They go back only to Leonhard Euler, or perhaps to Descartes if you are generous. But in fact, you can find them in antiquity. Most notoriously, Lucretius described the graph theoretic structure, what we would call the graph theoretic structure of diamond. So people have been thinking about materials in terms of what we would call graphs for a very long time. Now, of course, people started thinking seriously about the structure of crystals, as opposed to Lucretius simply sitting back and fantasizing stuff with Kepler. But my impression is that people really started thinking about graphs and materials really in the 19th century. And so at the upper right, you see that is a methane molecule. In the Smithsonian, this was before people started thinking about the geometry of these things. But the point is that if you focus essentially on covalent crystals, where, I mean, I'm assuming there's no physicist here who will complain that there's no such thing as a covalent bond. But if we pretend that there is such a thing as a covalent bond, then you should be able to represent molecules and atoms as graphs, where the individual atoms or molecular building blocks are the vertices and the covalent bonds are the edges. So, for example, at the lower right-hand corner, there is a picture I swiped from the web of carbon. And that is a critter called a geometric graph. It is a graph that has been embedded in three-dimensional space. And so once people, inspired by people like Alexander Wells, started thinking of crystals made of covalent, when people started thinking of covalent crystals as graphs, the question is how to classify them. And as a result of historic accident, and historical accident was that a critical number of people interested in the problem were in Princeton. People thought, well, you can classify crystal structures by graph isomorphism. Okay, so for instance, At the bottom right is our old carbon atoms. At the top is ice. And you will notice that they have the hydrogen bonds drawn in as well as the covalent bonds. And then if you ignore if you just have the hydrogen atoms ignored, what you get is something that looks like diamond. Could set up a one-to-one correspondence between the oxygen atoms and the carbon atoms, and a one-to-one correspondence between the edges, and everything would connect up the same way. So you could claim that ice and diamond had the same crystal structure. Whereas if you look at quartz, here you have the silicon and oxygen, and just as you made pretended the hydrogen was sort of disappeared into the bond, you consider silicon across the oxygen to a silicon to a silicon. So this is what mathematicians call a cycle, what chemists call a ring of 3 silicon atoms. There are no rings of 3 carbon atoms, so you would say that quartz and diamond are not isomorphic. There is no one-to-one map from silicon atoms to carbon atoms and double bonds to single bonds that preserves the edge to vertex incidence. So you would classify, while you would classify ice and diamond as having the same crystal structure, you would say that quartz has a different crystal structure. This creates a problem. I think I mentioned that the theoretical computer scientists, actually computer scientists in general, got very interested in graphs. There's a whole bunch of standard computational problems that reduce to graph theoretic problems. I think I mentioned this old result saying that any computational problem involving discrete structures can be reduced rather quickly to a homologous problem on graphs. So one thing you want to do is determine how hard it is to determine if 2 graphs are isomorphic. And around 1970 or so, Fred Cook came up with the dreadful P versus NP problem, and people immediately started wondering how hard some of the other problems they were working on is. And it's been over half a century since Richard Karp pointed out that the question of whether or not a subgraph can be embedded into another bigger graph is actually what's called NP complete. It is at least as hard, it is precisely as hard as any other NP complete problem. So we do not know if there's a fast way to resolve NP complete problems. The current guess is that if a bunch of very smart people have been working on it for half a century, the answer is probably no. But there's a loud minority that says, well, maybe we're not as smart as we think we are. At any rate, no one knows how to find a fast solution to the graph embedding problem. What about graph isomorphism? Well, we do know that graph isomorphism can be solved. It doesn't require quite exponential time. This is called quasi-polynomial time. The lowest we can get this exponent to be currently is 3. And incidentally, Babai and his archenemy Hegsworth have not published their results. You will find them posted in various places. The one published result contains an error. So people are still working on the problem. At any rate, it appears that graph isomorphism is hard. On the other hand, suppose you fix an upper bound on the valency of your vertices, something like 12. I am only interested in graph isomorphism for graphs whose maximum valency is 12. That is a p-time computable problem. And it's been known to be p-time computable for some time. And then shortly afterwards, 3 people got together and they discovered that if you take all of the graphs of, say, 25 quadrillion vertices each and put them in a bag and chose 2 of them at random, you could tell pretty quickly whether or not they were probably isomorphic, and this particular algorithm would almost always work. Now, this would not work for graphs that chemists are interested in, because even though if you're dealing with graphs of 25 quadrillion vertices, some of their valencies are going to be of the level of, shall we say, 10 quadrillion. So if you have, if you don't want things to be a very high valency, you don't want to use this particular algorithm, but it is a sign that there are algorithms out there that won't tell you for sure whether or not 2 graphs are isomorphic, but they will tell you, give you an answer that is probably correct. Meanwhile, we're interested in interested graphs. Okay, so we're approaching a thread that was launched in about 4 decades ago by Chung, Han, and Klee. And what they decided to do is represent graphs, infinite graphs, using just their unit cells, standard operating procedure, but a graph theoretic analog. Okay, so we have a large graph. This is suppose this is a crystal, and we have a group of automorphisms, so that when you divide the graph by the group of automorphisms, you get a small quotient graph. Then we can lift this quotient to become a tile on the large graph. And then you can tile the large graph with these appropriate preimages of the quotient. So, yes.
Greg, could I ask here briefly if you could explain in more details a group of automorphisms? For example, does it include the lattice group of all translations? Can it be more general? Simply for the benefit of our audience who didn't see these graphs previously.
Okay, so an automorphism on a graph is a function that maps the vertices one-to-one and onto from one graph to another, maps the edges one-to-one onto the other graph, such that the vertices of the endpoints of an edge are mapped to the endpoints of the corresponding edge. So it maintains all the connections. So if we go back, so there's an isomorphism from ice to diamond. You map this red oxygen atom to this black carbon atom, this red oxygen atom to this red carbon atom, and this edge with a silly hydrogen atom in it to this edge right here. And you do that for all pairs, all edges, and all pairs of incident vertices. And that will be one-to-one and onto map from vertices to vertices, one-to-one onto map from edges to edges, preserving the vertex to edge incidence relation.
Greg, could I ask about this diamond graph? Do you understand correctly that in this diamond graph, every vertex is connected to exactly 4 neighbors?
Yes, that.
Right. So the picture is smaller than it should be.
Yeah, this
right?
is a fragment of a diamond. Just this up here is just a fragment of ice.
Right. And similarly, in this ice graph, every red oxygen atom can be, well, abstractly connected to exactly 4 neighboring oxygen atoms.
This one right here in the middle that my hand is on is connected to one directly below, and it's connected to the one in front, and it's connected to 2 at the sides. So it's diamond, I've noticed, is a little bit difficult to see. You have to orient it properly. It's easier to see down here that this one is connected to 4. And the idea is that it extends in all directions infinitely far.
And in your last slide shown, your large graph gamma, is it an infinite periodic graph, or do you still consider a finite one?
You mean this right
The
here?
slide about automorphisms.
Slide about automorphisms. Well,
Yes, yeah,
automorphisms.
this one.
No,
Yeah, no,
this to this. Well, the thing is that the automorphisms of this thing, which are these are two are also isomorphic. The automorphisms. Okay, so returning to this one right here, the automorphisms on this crystal will be the maps of this graph to itself that are also isomorphisms. So they map vertices to vertices, edges to edges. It might be easier to see looking at this one. This these are valency 3, so they can't be mapped to the middle. So all of the automorphisms of this are going to be the dihedral group of order 4. So there is the rotation by 90 degrees, and there are reflections that also preserve the relation. So those would be the automorphisms. And you'd get the same automorphisms here. The difference is that here, the automorphisms are all preserve the geometry of the structure, but here, some of the automorphisms, like rotation by rotation around the base, will not preserve the geometry of the figure. But crystallographers are typically interested in automorphisms that preserve the geometry of the figure, and those are going to be the crystallographic group associated with that geometric graph.
Okay.
Does that help?
Yeah. Yes, I encourage everyone to ask questions if.
Yes, please ask questions. Don't let me sail off into the wild blue yonder. Okay. All right. So the idea is to represent the graph gamma with this quotient graph somehow. So here is a big graph, and it's a graph of very high symmetry. And incidentally, a lot of this stuff works in a field called geometric group theory. And the geometric group theorists have decided to work with directed graphs because that's the only way things work. And then they call them graphs. So this is technically geometric group theory, so that's what I'm working on. So a graph has a collection of vertices, a collection of edges, and then each edge has an initial vertex and a terminal vertex. So that gives you the initial endpoint and the terminal endpoint function. And then an automorphism maps the graph to itself. Now this thing, if you consider the orientations of the arrows, then this thing has the wallpaper group CM, but I want a group that acts freely, and CM would fix a whole bunch of vertices and edges. So I'm saying let G be the lattice group. So that's the group that maps this to this. That's one generator. Another generator is mapping this to this, pushing everything up one step or pushing everything to the left one step, and then get the group that you get out of that. Now, if I take that group and I divide by that lattice group, I get this quotient graph. And yes, this quotient graph bears a certain similarity to the unit cell. So the idea is all of the red edges that point up to the right are mapped to this edge. All of the blue edges on the left-hand side of this square are mapped to this particular. Oh dear, did I get this backwards? I think the arrows are backwards. I'm sorry. Yeah, this arrow should actually be going. This arrow. No, that is correct. Yeah, so the arrow is correct. So this arrow, for instance, right here is mapped to this arrow right here. And all of these arrows at this corner, this arrow right here is mapped to this arrow right here. All of these are mapped into their own arrows. So you have 4 orbits of vertex under the lattice group, and they are actually 5 orbits of vertex in the lattice group, 4 orbits of red edges, and 4 orbits of blue edges. And then what we do is we lift this quotient up here. So this is the lift, and you can think of this partly as a sort of bit of the quotient to lift up, and partly as a tile, because you may notice that you can actually tile this entire graph with copies of these lifts. So this entire graph here consists essentially of a whole bunch of lists of these things that cover the entire thing. And you'll notice,
Greg,
yes.
Greg, to do this lifting from
Yes.
the quotient graph to the periodic graph, are you using a unit cell in any way? So any geometry here used?
Okay, this is this lift is probably corresponds to what you see in the IUCR tables. It's you have a unit cell. Actually, a unit cell probably would look more like what I'm outlining right here, but that would require cutting across edges. So it really is, but it is analogous to a unit cell. And that was deliberate. We were trying to figure out determining group isomorphism in a way that is consistent with the usual way for identifying crystals. So this is analogous to a unit cell. It's done in such a way so that every single edge and every single vertex would be in exactly one lift. So you would get a particular lift that consists of these, and then these, and then these, and then adjacent to this would be another lift with these edges and these edges. And then adjacent to it is another lift with these red vertices and then these blue edges and these blue edges. So this entire thing could be regarded as a sort of tiling of all of the plane with copies of this lift. So that's what we're trying to play with. And the idea is to try to use these to identify, if you're given a quotient, try to identify what kind of crystal you're dealing with from that quotient. So here's a technicality, and that is we choose a particular tile in the infinite graph to be the reference lift, and then every other lift would be a result of applying an element of the lattice group, a translation, to this reference graph to plop it someplace else. So that's how we keep track of which lift is which. Now we have a problem. Suppose we have a quotient graph. We can get several different graphs would have the same quotient graph. Several different graphs would have the same quotient graph. In fact, this thing has this as a quotient graph. So the problem is we have a tile that's essentially a description of how to get a tile. That's the quotient graph. And we want to create the crystal out of it, but we need instructions on how to connect up the tiles. And for that, we need a critter called a voltage. So let's return to this picture. This is the lift graph, and you may recall I plop the lift graph. This is the reference vertex. And then if I want to plop the tile here, I want to move 1 unit to the left. That means translate 1 unit to the left. So I label these vertices with the 1 unit to the left to move from this tile to this tile. Similarly, if I wanted to move this tile up here, that means translate 1 unit up. So I would label these edges with move 1 unit up to go from this tile to this tile. So once I have those instructions on the lift, that tells me how to tile the entire graph. And then I plop those instructions on the corresponding edges in the quotient, and the result is a critter called the quotient graph. This quotient graph is in essence, a way to get the tile together with instructions on how to tile the entire graph. So the voltage graph will represent the original crystal structure. Okay, so this is the grand picture. We have the quotient graph, and it is lifted. That means go in reverse of this covering to get the tile. Then C maps this into the reference vertex, which then can be moved all around, and the entire shebang can then be mapped by this onto homomorphism onto this, and it's a very special kind of onto homomorphism called a regular covering. I'm not going to go into that right now. So this is how you can get the original graph from this labeled quotient called a voltage graph.
Greg, so another name for a voltage graph is labeled quotient graph, right?
Well, actually, if you go into the computer science community, you'll find them are called gain graphs. I do not know of anyone who calls them labeled quotient graphs, partly because there's another group of people, we'll talk about that briefly here, who, when they talk about labeled quotient graphs, what they're talking about is coloring the edges or coloring the vertices.
Not by these automorphisms, by something else.
By colors, yes. We get some paint and we paint them. We will be doing that shortly.
Okay, there is a question in the chat for you, Greg.
Oh, sorry, I should be monitoring chat. Sorry, what is? I do not see the question.
Would you like to ask yourself? Right.
I cannot see the question in chat.
Right. Well, maybe I could rephrase it a little bit more general. So what happens if you choose a different unit cell in the initial crystal graph or periodic graph?
Oh, yeah. There are you will get always the same quotient, but you could lift it. There's a whole bunch of different ways to lift it. You could have used 2 arrows down here and then 2 over here instead, or you could even use 1 arrow here, 1 arrow here. You had lots of different choices for what your tile is going to be. But you again, if you took that tile, made it the reference tile, and then used the same group to move it around, again, you would tile the entire thing. This is assuming that you have a group that acts freely on the crystal graph. If you do not have a group that acts freely, like a randomly chosen crystallographic group, then this will not work.
So the quotient graph will remain the same if you change a unit cell, but labels might change.
Oh yeah, if you have a different lift graph, then the voltages will change. And that's one of the difficulties that we're facing, which we will address, which is that you can have 2 different voltage graphs with the same underlying graph, but they have different voltages. And the burning question is, do they represent the same crystal graph? And we will get that to that in a moment. Okay, all of this I've talked about works only for these particular collection of crystallographic groups. It does not work for any of the others. Okay, so, but anyway, today we're only talking about P1. And in fact, the articles we're writing about only talks about P1, so we don't have to worry about any of the others. Okay, yeah, and here's a technicality. the edges that I have not labeled, we're just presuming are 0. So 0 means that I am mapping this lift to itself. Okay. Now, I think I should mention this is a picture that appeared in a previous talk, and that is you could actually just start off with a graph, a lift graph, and then randomly assign voltages to it, and then you would generate a graph out of that. And that actually is a situation that you're typically going to find. Your software is going to give you a pair of quotient graph with voltages labeled in, so it's a voltage graph, and that's what you're going to be playing with. And you can think about, how to generate a picture from that. Okay, the thing that you get from the voltage graph is called the derived graph. And there is a theorem that says that if you take a graph and get its voltage graph and then set up the voltages right and then derive the graph going through here, then here, you'll get back to the original graph. So this is actually a faithful representation of the crystal graphs, provided that you do everything right. Okay, so this is officially what the derived graph looks like. And now we want to go back to isomorphism. So we have two voltage graphs. And so what we deal with is the nicest situation when the two voltage graphs have the same underlying graph. So here we have an underlying graph, and you'll notice it's used to generate this thing, and you'll notice that I have assigned zeros to a spanning tree on the quotient graph. And if it's like that, we've gotten the habit of calling that condensed. Another paper calls them normalized. I don't know that there's any standard word for it. But if you start off with a condensed voltage assignment on a connected quotient graph, your derived graph will be connected. And incidentally, the way I've colored this, you may notice that these are colored with the successive lifts of this quotient graph. Okay, so this mentions that today I want to have assign voltages so that there's a spanning tree, all of whose voltages are 0 in the quotient graph. Okay, so this is the question that was just asked. Two groups of people, I think they did this independently. And I suspect that there's at least one other group of people who also proved this independently. But the thing is, suppose the quotient graph is connected, and suppose you have two voltage assignments that are condensed with respect to the same spanning tree. And the burning question is, are those derived graphs isomorphic? And the answer is yes, if there is an isomorphic, the wording is rather queer. So the basic idea is you want to have condensed voltages, and the spanning tree gives you a one-to-one assignment of voltage to voltage. And if that extends to a group isomorphism of the two voltage groups, then the two derived graphs are isomorphic. On the other hand, if it is impossible to get spanning tree, isomorphic to spanning tree, assignment of one-to-one assignment of voltages to extend to an isomorphism of the groups, then the two derived graphs are not isomorphic. So all you have to do is get hold of the spanning trees and then look at whether or not you get a group isomorphism. And that will tell you whether or not the two derived graphs were isomorphic. So this is an answer, and I have seen that crystallographers have already published stuff on this, even though it said crystallographers have forgotten what they published. So this is what happens if you have two graphs whose voltage graphs have the same underlying graph. Okay. Yes.
Greg, two voltage graphs with the same graph without any labels. You mean, right?
This is the voltage graphs are the graphs whose edges have been labeled with group elements.
Right.
So over here, this has a voltage graph whose quotient has been labeled with elements from one group. This is a graph whose quotient graph have been labeled with elements from another group. And the question is whether or not, if you can get isomorphic spanning trees, you get a one-to-one correspondence between voltages that extends to a group isomorphism from this group to a group isomorphism of that group.
Okay, so all graphs here are finite in this picture, right?
Oh no, the graphs in this picture, right now, what we're interested in is when we're dealing with P1. So these could be finite or infinite.
So I thought that the derived graph, so the quotient over all automorphisms, this is a finite graph.
No,
not necessarily.
returning here is an infinite graph. Its quotient is finite.
Yes.
But these are it's this group here is P1. It's generated by these translations, so it is infinite.
Of course, the group is infinite. Yes.
Yeah.
But the graphs are finite.
That's because if you're dealing with software does not like infinite graphs.
Okay. Right. Thank you, Greg.
Okay. Okay. Now here's an extra gadget, and this gives me an opportunity to mention when you talk about labeled graphs. This is what combinatorics people typically mean. This particular gadget we wind up using, and this would be an impediment for crystal analysis people, but it is something that is built in very often for crystal design people. The idea here is that each of these double arrows actually refers to a pair of edges, each one going one way, the other going the other way. So these actually refer to a pair of anti-parallel edges. So this is a pair of anti-parallel edges. And I've taken out some paint and I have painted every single edge blue, red, or black. And the thing is, you may notice that if you're at any vertex, you have exactly one outgoing blue edge and one outgoing black edge. Unfortunately, you have two outgoing red edges. So this is not a bideterministic labeling, but bideterministic labeling is the kind of thing that we want. If you wanted this to be bideterministic, it would have to be going one direction around. But so what we actually do is we have alternate colors. I should have colored alternate colors going around this cycle. But the thing is that once you have this, you are able to get around the graph isomorphism problem for finite graphs. So when you're dealing with quotient graphs, you don't have, if you have them bideterministically labeled, then you don't have to worry about automorphisms on those on the quotient graph. Because the only automorphism will be the trivial one. Okay, so let's take a look here. That was a brief aside. I probably should skip that. Here we have three quotient graphs and with the same spanning tree, but with different voltage labels. But you'll notice that these two voltages generate the even integers. These two voltages generate the integers. And the map from here to here and here to here extends to a group isomorphism of the integers to the even integers. On the other hand, this to this, the 2 to 1 and 3 to 1, does not extend to an isomorphism of the integers to the integers. So these two, the derived graphs of these two are isomorphic, but the derived graphs of these two are not. Okay. Now, this is actually proven formally later. If you have something, if you have a spanning tree, you can have different spanning trees to produce the same graph. And no matter what voltage assignment you get, if you have a spanning condensed or not, it will generate a whole bunch of copies of the same thing. Okay, but now our collaborator, I'm 3/4 of the way through, asks the burning question, which as far as I can tell was not answered. Suppose you were given two voltage graphs with different underlying graphs. How do you tell if the derived graphs are isomorphic? Okay, so I'm sure because I'm running out of time, I'm going to skip the thing that did not work. And why it did not work. Okay, so this is what we wound up having to do. The idea is, here is a nice graph, and you'll notice the coloring is such that for any vertex, there is at most one, and any color, there's at most one outgoing edge of that color and at most one incoming edge of that color. So this is a bideterministically labeled graph. Here is the quotient, here is the lift, and it goes up to here. And what we want to do is we want to go here. We're wondering if this particular quotient and this particular quotient have the same derived graph, if they have isomorphic derived graphs. So what we do is a computer algorithm that attempts to construct a voltage graph of for the common voltage graphs of these here, and see if this construction completes. If the construction completes, then there will be the two derived graphs are isomorphic. If the construction fails for some reason, the two derived graphs are not isomorphic. So the first thing we have to do is we have to go upwards. We have to find a graph that covers both delta 1 and delta 2. And so this graph that covers both of them, we get the vertices and the edges, and we find the thing that covers them both. I'm running out of time, so won't go into details on how to do that. And the construction is such that this is a minimal thing, so that if any other graph covers both delta 1 and delta 2 and is also covered by the two derived graphs, it will also cover delta top. So delta top will be the minimal graph that covers delta 1 and delta 2 and could work as a voltage graph for the derived graphs at top. If you can construct delta top. Sometimes delta top cannot be constructed, in which case you know that the two derived graphs are different. Then we lift the voltages from here to this and the voltages from here to this. So we get two distinct sets of voltages on delta top. Now we finally have two sets of voltages on the same underlying graph. And now we can use the Scoviero-Kim-Lee theorem to check whether or not the derived graph from the voltages here, namely this, derived graph from the voltages here, namely this, actually are isomorphic. And that will give us our answer. And incidentally, so far as we're able to tell, for technical reason, this works only if the voltage graphs are abelian. We are still trying to get around that. But since we are interested in P1, using P1 in our current project, that is not an issue. Okay, so the next thing we want to do is figure out how to get all kinds of details together with how to make this work with P1, but that is probably for a future talk. At any rate, here are the references that I referred to in case you are interested in tracking any of this stuff down. So that's it. Thank you very much. And are there any questions?
Thank you very much, Greg. Let us thank Greg for his nice talk, please. Okay, yeah, we have about 5-10 minutes for questions. So please, questions for Greg. Teddy, this research is closest probably to your interests, so yeah, feel free to ask.
Yeah, for that reason, I don't really have any questions except for the last bit. So can I have a quick look at that? Was that an example of two graphs? So was it 2 slides back, I think? Was it with the example? Sorry, yeah, this one. Oh,
This one?
This here.
Yeah.
You're saying that. Yeah, I wasn't quite sure I understood. I'm just having a quick look now. So you're adding extra edges for the lifting. You're not just labeling the existing edges, or
Oh, the thing is the lift graph has to be a graph.
that's what I thought. Yeah.
Yeah.
Oh, so
yeah.
right, I can't really see. I think I can understand how the tiling of the theta works now.
So yeah, the problem is that typically if you're going to have something that is precisely covers the quotient, it's going to be something that is not a graph. It's going to be a creature that is typically called a transversal.
Yeah, the transversal.
And so since we want to deal with graphs, I mean, there's a certain underlying category theory here, which wants everything that deals with to be a graph. So for that reason, we have these lift graphs.
I mean, sure.
But technically, we don't need this part or this part. Actually, we could cut off these and this and this. So this is a rather large lift, but it is still a lift, technically, from the point of view of topology. But you could get a larger thing if you are you asking about an example when you have 2 graphs with different underlying quotients?
Is that not what this example sort of shows, right?
This is a graph with one underlying quotient. Let me see. Let me get up Paint.
I mean, I don't. Yeah, no, I'm.
So the idea is if you took
I'm sure. I mean,
yeah. So if I took the standard grid, this is the standard grid, then one possible lift would be this. Another possible lift would be this. And in this case, the sideways voltages here would be 1, 0. And going up, it would be 3, Oops, it
0,
would be, sorry, it would be,
0, 3.
yeah, it would be
Yeah.
0, 3. But here what we would have going sideways is 2, 0 and 0, 2. So what Natasha would be asking is, how would you tell that these two lifts that correspond to two different quotient graphs? So this is what this quotient graph looks like, and this is what this quotient graph looks like, and they would be comparably have comparable voltage labels. How would you be able to tell if this long loop was 0, 3 and these three short ones were 1, 0, whereas over here you have 2, 0 and 0, 2? How do you tell whether that they are actually the same graph?
Yeah, sure. I mean, yeah, this isn't something I've worked on because I start with the full graph and then we find the smallest sort of quotient group. So in this case, we would just find a smaller one for both that would actually be equal. But that, like, sorry, not quotient group. Yeah. So the quotient graph would end up being. So
Well, the truth is that in this day and age, the crystal analysis people are so used to software that simply pop up something that looks like a unit cell, and then you get to decide what it is a unit cell of.
yeah, I think yeah.
But here with the crystal design people, then you do have a problem. You have essentially spaces of these things, and you're trying to figure out, is this thing actually the same as that thing? Is this a distortion of that thing? So you have to have more of a handle in it, these things. And very frequently, at least in the work I do, you represent the spaces with quotient graphs because that's what will fit in a computer.
No. I'm saying that both of these two examples on the left can each be represented with a smaller quotient graph that is equal.
Oh yeah. But then there's the question of finding in general an algorithm for finding the minimal quotient graph, and that can be done. You have to get your paws on the automorphism group of that quotient graph, et cetera, et cetera, et cetera.
Yeah, I've actually done some work actually on you're saying about this, where we're talking about, for example, the asymmetric unit cell. We're working with non-abelian groups. It doesn't work in the same way with the nice kind of
Oh yeah, non-abelian groups, all kinds of
groups.
unpleasant things happen.
Yeah, I actually done some work on it, but it's not in that paper. So if you're interested in that, we could talk about that. But
Sure. So yes, you are T. McManus.
Jonathan.
Jonathan McManus, the author of the paper that you read recently.
Oh.
Well,
Yes,
we talk
about bridge length.
So I just put my email in chat.
All right, nice. Oh, well, I can.
Yes, thank you. I'll actually stop the recording while